Hello, everyone, and welcome to the Hyperthesis podcast. You're here for episode 49, a very exciting episode, and kind of a continuation from one of our previous episodes, but you'll find more out about that later. To start, I'm Patrick.
I'm Pheely.
And I'm Liam.
Well, we have quite a range of topics to discuss today. This is a bit more of a disjointed episode, but that's even more fun to talk about. And to start, we will start with an intro topic, which I do have something right away to talk about, and that is undersea cables, especially for telecommunications. So we talked about this a bit in the last episode when we were talking about fiber optics and photonics and how fast we can get data to travel and how much we can get it to travel. Now, of course, data is limited by the speed of light. So when you're on your phone or when you're, say, on your computer connected to Ethernet that's then connected to fiber optics, you are limited by the materials and the speed of light that those systems are made of. And we discussed photonics briefly, but from that, we kind of delved into subsea cables a bit, and I did a bit more research, and there's a lot of cool things that go on with these cables. So, based on a bit more fact-finding, there are actually over 1.4 million kilometers of cables lying under the ocean floor, and this spans about 400 to 500 separate cables, all with their different terminus points. Some span the entire Pacific Ocean, while some span small distances, such as the English Channel. But the ones that span much larger ranges, they actually require some signal amplification. And so we discussed this a bit, whereas when you have these fiber optic cables with the light totally internally reflecting within these fiber optic strands, you do lose a bit of the signal for each reflection, which is known as evanescence. Now, this signal must be repeated so it's not lost halfway, say, through the Pacific, and this is done through repeaters, which are actually placed in the cable, I found out. So these repeaters, while being supplied with energy, are able to, or electricity, I should say, are able to amplify the signal and send it back out, therefore letting it transmit over longer and longer distances. Now, this is again done with repeaters, which are built into the cable, and I found out there's actually a copper layer in most of these cables that is able to power the repeaters. So not only is it transferring signals, say, from the internet or communication signals, it's also transferring a bit of power.
There's also could be a method to reduce the latency by at least 3 times, exactly like 3.1415 times, right? If instead of drawing cables through the surface, if we can just punch a hole through the core of the Earth, it's pretty much unrealistic, but that's gonna save you a pi ratio or pi multiplier of travel time, right? So that's, if you can do something like that, even because having cables through the surface, not, it's pretty far. And I think people also look into satellite, which is in a way further, right, in terms of latency, because you have to shoot up into the sky and come back. So I don't know, in terms of latency, what can we do unless we have like quantum technology, some kind of entanglement way to break that, which in a way is not really a thing.
I mean, to be fair, I think latency with undersea cables is probably the lowest it will possibly be, given that as of now, we haven't shown that information can actually be transferred faster than the speed of light. But in the case of cables, burying them also might be more and more expensive. So just as a reference, to lay down 1 kilometer of cable, so that includes the materials for the cable and then actually laying it down, on average, it's about $33,000 per kilometer. And now, mind you, undersea, they do kind of bury them a bit, but that's more so for protection. They aren't digging into the earth to make a straighter line. But they are still faster than satellites. Because if you think about it, if you send a signal, say, to a satellite, if you're using the Starlink network, which is the only working satellite internet that's publicly available. It has to go up to the satellite, interconnect between a couple satellites, and then down to wherever it's being transmitted from. So that's a lot longer path than sending it straight across the surface or even under the surface of the Earth.
Yeah, even though light travels slower in glass, I mean, maybe these optical cables are special glass, but and typical glass is like 2/3 its normal speed, I think. But it's probably, yeah, you have to have multiple satellites kind of interacting, and that takes time, and the signal going up and down very far. But you said there's like 1.4 million lengths of cable, um,
Kilometers. Yeah.
kilometers. Yeah, sorry. Is that just between? That's not just between the Atlantic, or sorry, in the Atlantic Ocean. That's all over, right?
Yeah, that's the total length of all undersea cables. So, like, again, there are about 400 to 500 cables laying on the seafloor, and they connect everywhere from like Canada to Europe or America to Japan. There are many different cables, and so that's the length of all of them.
I just did a little like calculation because I want to. I always try and compare things. Maybe I do that like imperial thing where I say like, here's a banana for reference. But I think it's the distance between Eastern Canada and Ireland, so the eastern part of North America and the western part of Europe. That's enough cable to stretch back and forth about 350 times between those two, which is pretty crazy to think about. That's a very long cable. Or, well, I know it's
Yeah.
not just one, it's a lot, but like if you stretch it end to end, it's a lot.
Oh yeah, it's can go to the moon and back many times. But it's funny you should mention the transatlantic cable going from the east coast of Canada, which is the furthest eastern point is in Newfoundland, and then the furthest western point that's closest to Newfoundland is Ireland, or an island just off the coast of Ireland. And this was actually where the first transatlantic cable was installed. Now, at that point, it wasn't fiber optic cables, but instead copper cables that were used to transmit Morse code. For telegrams, which we don't have anymore, and I think aren't in use anymore. I think the last telegram was in India a few years ago, more recent than you think. But these were to relay messages between Europe and North America over a copper cable. So this was a lot trickier than fiber optics, at least in terms of transmitting the signal, because you had a lot higher signal loss at that point. Because instead of sending light through fiber optic, you're trying to send a high voltage, or at least a voltage or a change in voltage through a copper cable. So over distance, that voltage decreases, and at that time, it was very hard to amplify those signals.
Yeah, just to note, like, how does it decrease, right? Because it just dissipates into heat, basically. If you want to send like electrical signal, basically, it's gonna, it's gonna leave residues, right? Like along the line as heat. So that way, it's like, it's really tough. Where when it's light, the loss is much more controlled. Like, the system much more close.
Yeah, and that's an issue, is how do you deal with the heat? You are surrounded by ocean, which is helpful, but you also have to have a very good insulating layer, both electrically insulative, because of the fact that you're in seawater, which is also conductive, and then also to make sure that nothing happens to the cable. So this first cable, which was laid in the 1850s between Valentia Island off the west coast of Ireland and the Bay of Bulls in Newfoundland, it was laid essentially just copper with this very interesting insulative layer on top of it. And there's a whole history behind that I won't get into. But it was actually worked. I believe there's where they called historical minute about it, which is like Government of Canada produced short clip of historical Canadian moments. But the first message sent was from Queen Victoria to the President of the United States at the time, who was James Buchanan. And so this cable didn't last for all that long. It was dead quite quickly, just because it wasn't designed the best. There were a lot of malfunctions, and putting too high a voltage in it essentially is thought to have what would have broke it. But regardless, this cable was the first, and now instead of having copper cables, we have these very highly manufactured undersea cables that have many layers of protection, and they can have 200 or more fibers at their core. So it's not just one glass fiber that's going along, it can be hundreds of these fibers going along, which increases the bandwidth. And I believe the highest transfer rate for a cable is for the new Maria cable, MAREA, which is just an acronym, and it's capable of transferring 224 terabits per second, which is insanely fast. These cables are.
I wish my internet was that good.
Good luck in Canada.
I know the amount of data from particle accelerator is quite a bit too. So in that term, those cables not that is really high, but the amount required for like real research, top tier research, is just unreal. I think Patrick, you know more about how much data needs for kind of like comes out of those accelerators.
Yeah, I mean, this is a huge problem with these particle accelerators is the amount of data that's produced from them. So Atlas, which is the particle detector found at the Large Hadron Collider, it is just an insane amount of data where they need petabytes of storage of these data. And for reference, most phones and most computers are at the gigabyte to terabyte range. So petabytes is 1,000 terabytes. And yeah, it's petabytes and petabytes of data that are produced by these detectors. But again, it's not produced all at once, but you still do need very high bandwidths to be able to transfer the data from all the detectors, especially these ones that are the size of buildings, to the computer system. And there's a lot of information handling and sorting and filtering that's done.
Yeah, I was gonna say, like, at CERN, they get so much information, but there's like a whole branch of like data management science that just goes into like filtering out kind of the useless data they collect from these particle detectors and trying to only get the interesting stuff so that you still have a lot of data to deal with, but it's significantly less than it would be if you just kind of took everything. And that's very helpful for them, I think.
So going back to submarine cables, one final thing I want to mention is just how layered they are. So it's not just this fiber optic cable with like some steel strands around it, but they are thick, as Liam has pictured, which you can't unfortunately see. So these are very thick cables with many different layers. Of course, the fiber optics are at the very center, covered by either petroleum jelly or some sort of silicon jelly substance that's protecting them, and then also prevents or it increases total internal reflection, so none of the signals escape. But then there are also many other layers, including ultra high strength steel wire housings, which are wrapped around to provide strength and stability. There are anti-crush layers that prevent it from being crushed under such great and immense pressures. There's polyethylene layers to inhibit static and corrosion. There's, of course, the copper layer, which is used to pass electricity through it. And typically on the very outside are tar-soaked nylon layers. So these are very large ropes that are wrapped around quite tightly to protect the cable from harm. And there's evidence of boat anchors being dropped and severing cables, or some different types of fishing, which dredge the sea floor, have cut cables. There's also been a case or two where a shark actually bit a cable and it disconnected. That hasn't happened since 1985, but since these cables are many kilometers deep, there's also lower risk for like the trans-Pacific, transatlantic ones and the more major ones. But there is still a chance they can be severed. But given that we have 400 to 500 cables already, if one is severed, that just means traffic is rerouted differently, and they do have repair methods for these cables that they can do quite quickly.
Yeah, this is like a feat of engineering for humanity that people don't talk about or know that much. So
Yeah,
this,
that's what I was. That's when I brought it up during that other episode. It kind of came to in my head. I was like, wait a minute, like I've heard of these things before, but I never really put much thought into them. But it sounds absolutely crazy, like how much effort and technology you need to make this, like these, like the bottom of the ocean, just the pressure alone, let alone creating a cable that goes so far and does so much. Like it's kind of wild.
Yeah, no, it's certainly quite the feat of engineering. And the fact that we're getting higher and higher bandwidths with these cables is quite impressive. And maybe we'll see the photonic chip that Pheely talked about last time in these cables or working at the ends of these cables eventually. But for now, we should move on from this intro topic about submarine cables to Liam, who is here to do some more star studded talk.
Yes. So I think I don't remember what episode it was. It was a pretty recent episode where I talked about these exotic stars that are stars kind of made out of this exotic material, like quark stars.
you mean last episode?
Was that last episode? No, it wasn't. It
Is
was
it
It
not?
was 2 episodes ago, episode number 47.
yeah. We've been doing double recording, so I guess it might have been like the last recording we did, but not the last
All
episode.
right, yeah, we did photography last one, yeah.
Yeah. But so I talked about exotic stars a bit, and then we also had an episode where I talked about Planck stars, which are, I really like the idea of Planck stars, but I won't get into that. Um, and I mentioned that I want to talk more about other types of hypothetical stars because hypothetical star, it's a star that we haven't seen, and it's shown up in theory, but we haven't directly observed it or probably can't, which I'll explain in a few minutes. Um, but they're not necessarily made out of exotic material. So I'm going to talk about hypothetical stars today that are not made out of these fancy, weird particles. More just regular star matter, I guess. So the first one I want to talk about, and I'm going to kind of have to indirectly talk about a bit more common stars to kind of explain where these stars come from, which Patrick might have talked about before, but that's fine. So the first hypothetical star is called a blue dwarf star. It's this class of star which can develop from a red dwarf after it's run out of most of its hydrogen fuel supply. So first off, I'm going to say what is a red dwarf? A red dwarf star, it's the smallest and coldest kind of typical average star that you can find. Um, and they're by far the most common type of star in the Milky Way, according to our current theory. So they're predicted to make up about 3/4 of all the stars in the Milky Way, and they have a very low luminosity, so they're actually pretty hard to observe. Um, One example is that for example, from Earth, none of the stars in the sky that we can see, which that are visible to the naked eye, are red dwarfs. Although there is some debate over exactly what the definition of a red dwarf is, so maybe some of them you could argue are on the border of a red dwarf, but I'm not going to get into that. And actually, Proxima Centauri, which is the nearest star to our sun, is about 4.2 light years away, which in kind of um, astronomical distances is basically touching us. It's a red dwarf, so we can see them, although they're pretty dim. Um, they're pretty small and cold, so red dwarfs can have a maximum temperature. And again, there's other people argue about these definitions, but I'm just going with kind of the most common one I could find. The maximum temperature is around 3,900 Kelvin with a maximum mass of about 0.6 solar masses. So they're less than 60% of the mass of our sun. And there's many stars much greater than our sun. So that's pretty small. But back to blue dwarfs. So blue dwarfs, they come after a red dwarf. Um, and they get their names because like red dwarfs, they have low masses, but they're blue. So specific red dwarfs, those with less than 0.25 solar masses, are believed to slowly increase their radiate, to slowly increase in how much they radiate over time, which will actually increase their surface temperature and they'll become bluer. Um, Despite this, blue dwarfs don't necessarily have to be blue, but the idea is that they get a little bit hotter. Um, over time. And since red dwarfs, they slowly fuse. They slowly go through this hydrogen supply and form into blue dwarfs, but they do it very, very slowly. It's actually predicted to be their red dwarfs are predicted to have lifespans of around trillions of years. And our universe is only about 14 billion years old. So we're probably never going to see them in our lifetime, but they're a theoretical prediction of the end of a red dwarf's existence. So it's just kind of a colder, smaller, or sorry, not colder, like a hotter, smaller blue dwarf or red dwarf. Sorry.
That's interesting to hear because, like, like 13 billion years old, like to us seems long, right? Like, but is it if compared to the age of star, it's not that long, isn't it? Imagine if human, like we last like at most more than a little bit around 100 years, right? And the universe much longer, like much older than us. But for stars, it's like the Earth is just a few years old, and the stars can last like hundreds of years in that relatively in that sense. So in a way, universe quite young. If it's the universe really old compared to the stars, a lot of stars would have died. I mean, like to go through all the process of turning to other stars already, and a lot of black hole would have formed. I guess more black holes. So in a way, this universe, in that sense, is quite young, isn't it?
Yeah, like we're, I guess we're kind of at the beginning stages of the universe. Well, it depends who you talk to, but all these hypothetical stars I'm going to talk about today, they're all stars that are predicted to occur like a very, very long time from now. And the trillion years isn't actually that long compared to some of them. um, but even like I just Googled, like, what's the lifespan of the sun? I'm not sure when our sun formed off the top of my head, but Google tells me it has about 5 billion years left of its existence.
And it's about 5 billion years old.
Yeah,
So we're
so
about halfway.
the universe is 14 billion years old. Our sun will have a lifespan of 10 billion years total. So that's like,
Yeah, so
yeah.
it's really young,
And
right?
there's
So imagine, yeah, like the Earth, right? Like compared to us, it's like many times over, right? In the factor of what, like, like of a million, more than like of 10 million or something, right? Like by the factor that the Earth can be older, like older than us. But in the factor of the stars, oh, universe is not that much older than the stars. Like
mhm.
it's really early. It's like the baby universe things still just start to happen.
Yeah, and even like there's stars called white dwarfs, which I'll talk about a bit in a moment, but there's white dwarfs that have
Are they all
existed.
dwarfs?
Most of these kind of there's dwarf stars that aren't hypothetical that are real. So like white dwarfs are an
Yeah. But
example. But
are most hypothetical star dwarfs?
yeah, because I guess it's something to do with the end of a star's life. They kind of, I guess, if they don't go supernova and blow up into a bunch of random particles, or they don't form a black hole or a neutron star, they end up kind of forming into one of these smaller dwarf stars for whatever reason. I don't know off the top of my head.
Yeah, larger stars tend to be unstable and don't live for as long. And essentially, if it's not forming a neutron star or a black hole, it will form a white dwarf.
And even if it goes supernova, the remnants of that gas eventually will form a dwarf star a lot of the time as well.
So in a way, dwarf stars are like a more stable phase of the stars. So basically, stars we see are basically in like a kind of metastable state where it's not really stable. It's metastable, right? It's not unstable, but the more stable phase of stars actually the dwarf star. Some could say that's the true state of the star
Yeah,
that it would be for a very long time. So in a way, the sun is in the process of being born. In a way,
yeah. I think
well,
everything's about.
the dwarf stars that would come out of the sun is the true sun.
I think everything's about time scales, right? Because it's like it's stable on some time scale, which is massive in our eyes. So it's effectively stable. But maybe if you're some cosmic god, the time scale of a star is very tiny, and that's like a blip or something, right? I don't know.
Just as a general rule of thumb, just for stability of stars, is the smaller they are, the longer they live. So these red giants or blue giants that we have will be around for like maybe 1 million years, whereas our sun, which is kind of medium sized, it will be around for about 10 billion years. White dwarfs, trillions of years possibly.
Yeah, but the sun would turn into some kind of dwarfs, right?
A white dwarf, yeah.
Yeah. Yeah, so in a way, it's like imagine if you look at it from like a cosmic perspective. If the sun is like the baby, and the adult star is the white dwarf. It would
Mhm.
turn into the sun is in that white dwarf is being born, and that process is what we see as the sun, right? Because that in terms of trillion years, like 10 billion years of the sun lifespan is like tiny first early part of the entire lifetime.
Yeah, exactly.
And if you are listening and disagree with that, stick around to find out how you can contact us.
um, one thing I didn't really understand, I didn't read into it too much. I'm sure somewhere could have explained it, but somehow these blue dwarfs, which are kind of like the next stage in a red dwarf's lifespan, somehow they get hotter, which I guess if you ask, like, I guess that happens with some stars. They go supernova and get hotter, but eventually cool down. But if you asked me to like make a naive guess, I would have guessed that the end of a red dwarf lifespan, it would get colder, but somehow it gets hotter. And there's physics that explains that. I didn't look into it, but I thought that was kind of interesting that a red dwarf becomes a blue dwarf, which is hotter. It's something to do with surface area, as it kind of burns through its hydrogen. But if you're interested, I recommend looking into it.
And these kind of processes are all nuclear, right? Mostly. And
There's
it
one I'm
must
gonna
be.
talk about which isn't, but I'll come to that. Or maybe there's
But
two.
that's hypothetical, right?
Yeah, well, a blue dwarf's hypothetical as well. You know, we don't have a few trillion years to wait and see one.
Yeah, maybe somehow in the future we might be able to do some simulations that confirm that. But
Yeah,
I don't think we have any capacity right now.
I think people have done simulations on this stuff. Um, but I don't know. I'm pretty sure they have. At least a Wikipedia page said there were simulations. But um, also, you know, our theory of the universe could be wrong. I mean, it's pretty solid, but there's a lot we're missing. So it could be that the universe is actually older than 14 billion years old, although there's not much evidence at the moment to support that. But who knows, right? Like, you never know.
Yeah, maybe one day we be able to break open the cosmic horizon, right? Because in a way, the fact that we postulate is to be almost 14 billion years old is the fact that we kind of found this place that we cannot observe more. If maybe it's not out of question entirely that we would not be able to break that barrier, that we'll be able to, see past the 14 billion years, which I think is highly unlikely. But we believe many things in the past that are highly that we like what we believe now can be thought of unlikely in the past.
Mm.
There is also other evidence for the age of the universe, but
Yeah,
going
like,
back to stars,
it all looks like it comes from the same place, kind of thing. But yeah, my point was that like a theory is a theory, and the predictions it makes only make sense within that theory. um, but it seems to be a pretty good theory at the moment. Um, so the next star I want to talk about, I don't have too many to talk about, but they're all kind of the same. They're all like a very long time from now, some star turns into another star. Um, at the end of its life. So the next one is not a blue dwarf; it's actually a black dwarf, and they're predicted to be the final state of a white dwarf star. So it's kind of similar to the previous one. And that's one a white dwarf is what our sun, like I think Patrick said, it could turn into one day because it's too small to become a black hole or a neutron star. White dwarfs, before I talk about black dwarfs, are remnants of lower mass stars, like our own sun, and they're composed mostly of electron degenerate matter, which for the physicists is just a fancy way of saying electrons in degenerate energy states. Now, again, I haven't done the math or physics of that before. I'm just trusting what the internet tells me, so citation needed. But usually these websites and Wikipedia as well are pretty accurate. The people who keep them updated in the physics community. But white dwarfs, they're these very dense and small kind of it's small in size, small in mass stars when compared to our sun. Um, so yeah, they have masses comparable to our sun, but volumes comparable to the Earth, all while having a very low luminosity, which actually comes purely from the emission of residual thermal energy or black body radiation. Right? Is that correct? I'm reading. I I didn't get to fact check this, but I read that these white dwarfs, they're just thermal radiation. There's no fusion or anything happening in them.
Well, I just want to put a note on the wiki stuff. In fact, like I remember at a conference, they have some kind of wiki edit-a-thon. So it's basically like a big event where like I think this time was all quantum based stuff in Wikipedia, and we get all the experts or people in the research area to sit together, and basically it's like a marathon but for editing Wikipedia. So some of these are actually like writings from experts in the area, people who know they're talking about. It's
Mo-
not just like it's not just random guy, right? So
most
this
of
is
them,
pretty okay.
yeah, most of them are from actual scientists who go in and edit them. And actually, that's a really cool idea, having a wikiathon. I should try and convince people in my field to do that, actually. But yes, white dwarfs, they have no fusion going on. So the sun's spent up all of its fuel. I just double checked that. I read it earlier, and now that I'm reading it again, I doubt it myself, but I went and double checked it. So the light that a white dwarf gives off is purely kind of black body radiation effects. Maybe there's some extra things going on, but there's not fusion reactions creating the light. Yeah. So the one example of a white dwarf, the nearest known white dwarf is Sirius, or is it Sirius? Sirius B, which is about 8.6 light years away. Eventually, however, a white dwarf will cool down by emitting thermal radiation through black body effects, but this takes a very long time, and the predicted star that comes out of that is a black dwarf. Your white dwarf, it comes in the thermal equilibrium with the universe, and eventually cools down and becomes black. And black in the sense like a black hole, that it'll emit very little light, so you can't really see it when it's in space. But this, for our sun, this would take for an star like our own sun, this would take a very long time, roughly a quadrillion years, which is 10 to the 15 years to reach this state. So again, they're a very theoretical prediction, and it's way too early in the universe's lifespan to confirm or deny this. But if they were to exist, they would be challenging to detect because of how little radiation they emit. And there also is a lot of speculation still going on regarding these stars. Um, like that we don't these kind of predictions don't take into account things like dark energy or dark matter or stuff we don't really understand. So the pictures could change in the future. But that's kind of like the current idea of a black dwarf.
Well, I think when it's really long, when they actually run out of zeros and you put like 10 to the 15 or something like that, like 10 to 20, 10 to 7. 10 to 7 is not far high, but like
Yeah.
a lot of people, well, not a lot, maybe some people would not be familiar with like 10 to the 20. It sounds like unrealistic, right? But is it? Right? Like in a way, like our body have like more than 10 to the 23 molecules, right? Like
Oh,
that's
way
just
more than
in
that.
a way, in a way, an absurd amount. It's not that many more. I think it just let me think quickly. Probably around like 10 to the 27, 28 molecules,
I
right?
just googled the human body contains about 10 to the 27. Yeah, there you go.
See, because one mole is like
Yeah.
6.022 to 10 to the 23, right? And you just and there's like how many grams and how
Yeah.
many kilograms in the body around.
Oh, sorry, it was
So it's
10,
all the
10 to the
magnitude of it.
25 molecules and 10 to the 27 atoms. We have an excuse. I haven't looked at a mole
Well,
since high school chemistry.
sometimes we just like to approximate. It's fun.
Yeah, exactly. But yeah, like these numbers, they're big. Um, but again, they're very big numbers out there, and we've talked about big numbers before, and I don't remember what episode that was, but they're small compared to the big numbers. The final star. So I have one more star, and then I have a little bonus. that I want to talk about. But the final star, all right, this trillions and billions of years are nothing in comparison to its lifetime. So it's called an iron star. Um, and it's this hypothetical type of compact star which could occur a very, very, very long time in the future from now. About 10 to the power of 1,500 years from now. 10 to the power of 1,500 many years from now, it might occur. And that's so long that you have to kind of ignore the fact that protons decay for this star to actually exist. So proton decay is this. So things decay. That's nuclear physics. Particles decay into other particles, and proton decay is something that's predicted, but physicists are still trying to detect this experimentally and even understand it theoretically. It's not agreed upon whether a proton actually decays. And currently, I think the accepted time it takes for one proton to decay is about 10 to the power of 34 years. So that's a very, very long time. Um, much larger than the age of the universe, of course, but much shorter than 10 to the power of 1,500.
Well, we talk about a little bit about decay time in the heat death of universe episode, right? Like, what's the projected um, time or like lifespan of the universe? And yeah, I think there's still a bunch of debates about it, but it's in the far future, way, way farther, like further than any human lifespan, or like I'm not even sure we will survive the next 10,000 years. We should, but we will see what happens.
In principle, we can, but realistically, will we? But anyway, so the idea of this iron star was actually in 1979, Freeman Dyson, who's a famous scientist slash physicist, maybe you've heard of Dyson spheres, but he's come up with a lot of other really cool ideas. He pointed out in a paper that if proton decay does not occur, then for stellar matter, so stars, all of the normal kind of light matter that these stars are made of, so like hydrogen, helium, lighter elements, it'll eventually spontaneously fuse into iron, specifically iron 56. And it will take about 10 to the power of 1,500 years to do so. And this will actually occur due to quantum tunneling. And I don't know why that is. And I couldn't really find a good explanation on it. So maybe I'll try and figure that out in the future. But it's interesting how quantum tunneling always kind of pops into things eventually. There's also a topic I want to talk about called false vacuum decay, which is kind of how it's a theory about relate to how our universe formed, and that involves metastability and quantum tunneling. So it's just interesting how this stuff, even though it shows up in like kind of atomic physics, it ends up relating to like more cosmology and planetary and star formation and things like that. But anyway, somehow all of these, due to quantum tunneling, all of these kind of lighter elements in the stars, after many, 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 many years, 10 to the 1,500, they'll form into iron 56, and then the heavier elements will also form into iron due to fission and alpha particle emission. So all the light elements become iron, all the heavy elements in the stars become iron. Um, So all of these kind of stellar mass objects in the universe eventually become these cold spheres of iron after a very long time. So that's the idea of an iron star.
It's interesting to hear that too, because like you remember the periodic table, right? Like iron's kind of in the middle. Is there a correlation to that, or I don't believe it's a coincidence because it's transition metals has very interesting properties. That's why I think iron's super useful, right?
Patrick, I think, wants to talk about it. I'll say I know very little about it, but in star formation astronomy, they have their own table of how they have this table that talks about it's not quite a periodic table, but it's a table of elements regarding star formation, and somehow iron is like it's a local maximum or something on that table. So Patrick, maybe you know more about it.
Yeah, exactly that. So essentially, iron is the most stable element, especially iron 56. And that's because any elements that are lighter, they will release energy when they fuse. But if you go more or if you're more massive than iron, then it takes more energy than is output um, when those atoms fuse. Going the other way, if it's heavier than iron, it will produce more energy when it fizzes or when it's fissile. Um, so nuclear fission with like uranium, which is much heavier than iron, is something that's quite common. However, as you get closer and closer to iron, it becomes less energy productive until you go lighter than iron, and then you need more energy to split an atom than what it would produce. And so that's why iron is the most stable element. And there are a lot of other reasons for this that we won't get into. But essentially, it's kind of at the point where fission and fusion meet, and going on either side each way will be less energy efficient.
Yeah, so that's why iron kind of ends up being the last remnant for these iron stars. And so, yeah, this is a very famous plot, um, or a few famous plots in astrophysics. And I remember learning about it a very tiny amount during our undergrad, although I forget most of it, but exactly what Patrick said. And if you Google Iron Peak, there's a wiki page that talks about it a bit and has kind of two plots on it. Talks about this binding energy and why iron ends up being the kind of choice element. But yeah, so that was Freeman Dyson's idea that eventually all these stellar objects will become these cold balls of iron in space. And it takes so long that if the proton decays, then something different will happen. But if the proton doesn't decay, then you'll get iron stars. So again, way too long for us to ever kind of check this. Um, but maybe you can do simulations to learn about it.
Just something before you move on to the final star, or I guess not so much a
My
star.
bonus.
I do just want to mention one other hypothetical star, which I learned about kind of recently, but it's very cool. And these are known as quasi stars or black hole stars. Now, these are also hypothetical. We don't know if they existed, but they are stars that may have formed in the very early universe that led to the supermassive black holes that we see. And essentially, the theory goes is that these stars, which um, formed when the universe was a little bit denser, everything was a little bit closer together, so more matter could kind of coalesce into this star formation before it blew away, which is what we see with star formation today. These quasi stars were essentially able to collapse and collapse. And meanwhile, more matter is coming on top, and they're just collecting these vast amounts of mass, mainly just hydrogen and helium. This was the early universe, so heavier elements didn't really exist. And they would be at least 1,000 solar masses, or 2 times 10 to the 33 kilograms, which is another very large number, but 1,000 times the mass of the sun. And so what would happen during the formation of these stars is the core would actually start to collapse because there's just so much mass there that the core would collapse into a black hole. However, the rest of the star would remain the same. So you would have a black hole at its core, and then these denser and dense layers around the black hole, and then essentially it would be formed very similar and appear quite bright, but still normal to a similar star. But they actually have black holes at their core. And then eventually it would all collapse, and some of it would dissipate, therefore leaving the black hole behind, which might have been our black hole at the center of galaxies. So these are very cool stars that we don't know if they existed, but would be very metal to have a black hole inside a star.
And I kind of like that theory because I don't know, it makes sense because where do supermassive black holes come from? It's not entirely agreed upon because if you think of a black hole just eating stuff or like regular galaxies, even like eating entire galaxies and things like that, a lot of them aren't big enough to make them the size they are now. Um, so that's a very interesting one. And at first I thought, well, wouldn't the black hole just absorb the whole sun really quickly? Maybe, but also our own sun, like again, it's all about scales. So you think like 1 ton, like 1,000 pounds, or 1,000 kilograms, whatever you want to call it. That's a lot of stuff. but our own sun fuses 620 billion kilograms of hydrogen into helium every second. That's like that you can't even comprehend that amount of kind of stuff happening, right? Like, so I don't know. It's just cool to think about the universe and stars and black holes. It's all kind of really mind blowing to think about. It's hard to keep a physical picture in your head sometimes.
Yeah, the scales are huge. And just one final thing about this theory is that these stars would be about 10 billion kilometers in radius, or about 20 billion kilometers in diameter. So their diameter would be about 130 AU, or 130 times the distance between the Earth and the Sun. So truly massive stars if they did exist, but still very cool all the same. Actually, they're hot. They're about 10,000 Kelvin, but still cool.
I don't even think that's hot, but that's not like crazy hot for a star, is it? I don't know.
I mean, the surface of our sun is about 5,500 Kelvin.
Okay. Anyway, I better move on. We're running out of time. I wanted to bring this up. This last kind, it's not a star, it's my little bonus topic. Because we talk about black holes all the time. Um, but there's these things called white holes, it turns out, which they're interesting. And I feel like I should mention them for once. We might have mentioned them briefly in the past, but I wanted to talk about it in a little bit more detail again. So, in general relativity, which doesn't take into account quantum mechanics, a white hole, it's kind of like the opposite of a black hole. It's this hypothetical singularity and region of space-time, which nothing can escape, or sorry, nothing from the outside can enter it. So, if you think of a black hole, it's black because no light or anything can escape from within it. Everything gets pulled into it if it goes past this event horizon. Their solution of Einstein's field equations, but you also get this time reverse solution, which is kind of the opposite. So if you're inside the white hole, no matter what you do, you get pushed out of it. So it's literally just the opposite of a white hole, or sorry, a black hole, and it's white because everything comes out of it. When you don't take into account quantum mechanics, of course, and that's also a solution to Einstein's gravitational field equations. It turns out, though, that for black holes that form due to gravitational collapse, this solution doesn't exist. So you don't see white holes in our universe because all of the black holes we see are presumably from some star collapsing, or maybe there's all these other ways they might have formed, like we talked about. But it's due to some kind of a bunch of matter getting really dense. So somehow, because of that, white holes aren't these physical things as far as we know. But like a lot of math, they show up and they might mean something deeper. So there's a lot of these theories about like parallel universes and how the universe could be a black hole and the formation could be like a white hole, or inflation might be a white hole from a previous universe. I don't know, but it's all kind of interesting stuff. So like black holes, white holes have kind of the same properties as black holes. They have mass, charge, angular momentum. Matter's attracted to them, like it is for any other form of mass or like a black hole. But the objects falling towards them never actually reach the white hole's event horizon. So they get like turned around, or they kind of approach it infinitely close but never quite reach it. However, if you take into account quantum mechanics, like Hawking did for black holes, you get this kind of reverse Hawking radiation. So we've talked a lot about Hawking radiation in black holes. But since a white hole can be thought of as a time reverse black hole, instead of a black hole emitting radiation, so it's not quite as black as we thought it was, this Hawking radiation, a white hole would actually absorb radiation, even though classically it shouldn't be able to. So it kind of like reverse Hawking radiation, which is kind of neat in its own regards. Just as neat as black hole Hawking radiation is, since it's not supposed to be able to absorb anything. And I know we haven't seen one, like we've seen black holes, well, indirectly seen them, but we haven't seen white holes. They're a bit less physical. But I know in these analog systems that I study, in this field of analog gravity, white holes appear all the time, except with sound waves or other waves. And it turns out most of the time, whenever you create a black hole horizon in an analog system, you kind of indirectly produce white hole horizons in the process. So in analog systems, there's something we can study and test and, verify, at least an analog system for Einstein's theory or even like theories of quantum gravity. Um, but yeah, I just wanted to point these things out because they're mathematically valid, but we haven't in certain situations, but we have no kind of actual evidence of them in gravity, at least.
Well, it sounds like if you do happen to find a white hole wherever you are, please report it to your nearest physicist, as we can prove then that they are physical and exist. Um, so thank you very much, Liam, for that main topic on stars. So we looked at theoretical stars or hypothetical stars and also exotic stars. So who knows what other stars we might look at in the future. But if you do have suggestions for the type of stars that you would like us to look at, or if you're an expert in stars, if you're an astronomer or an astrophysicist, we would love to have you on the show. And you can contact us multiple different ways. The first and foremost being our Gmail account. So we're hyperthesispodcast@gmail.com. You can send us an email with suggestions, comments, questions, or again, if you would like to be on the show, we would be more than happy to have you if you are an expert in your area. We can also be found on Instagram, where we are at the Hyperthesis, and you can find updates about when we post episodes, as well as some memes and some other updates. We typically take a couple breaks during the year. We're all PhD students, we're all busy, so we update when we're taking breaks and when we will be resuming recording and posting. We are also on YouTube. You can check out some of our back catalog there and share us with your friends. And of course, we are on pretty much every podcasting service: Apple Podcast, Google Podcast, Audible/Amazon Music, and we are hosted out of Spotify. So however you listen to your podcast, feel free to share us, rate us, subscribe, do whatever you need to do to keep listening to the Hyperthesis, and feel free to share it with people, whether they're your friends or your enemies. And to end today's episode, we have a story from Pheely.
Well, I thought we already had a story from the white hole from Liam, but I'll slap on another one. So since we've been talking about stars, I want to talk about the story of astrology. It's not
no.
astronomy.
Astrology,
It's just
right?
interesting because in terms of epistemology. Oh no, sorry, etymology. It makes more doesn't make much sense because logos is this logic and knowledge, and but nomos is convention, right? Things that we agree on. Somehow astronomy is facts, and now astrology is supposed to be using logic is kind of arguably untrue.
Yes, you have to be very careful talking about astrology. One, you were there for this, Pheely. I don't want to interrupt your story, but we went to a physics conference in Ottawa during our undergraduate degree, and they were voting on which university would host the conference next. And so each university sent a representative up to give a speech about like why you should vote for their university. And I forget which one, but one of the universities, the the person presenting accidentally said, like the physicist student presenting accidentally said astrology department instead of astronomy. I mean, I don't know why. Maybe she was having a conversation about astrology with her friends or like with their colleagues or something recently. But that university was going to win the vote, and this person accidentally said astrology instead of astronomy. And like, they're a physics student. They know the difference. They clearly believe in one of them. It was just a slip of the tongue, and the vote instantly just changed to the other university. The other university won because they accidentally said astrology. And I think that's so silly, but it's also quite funny at the same time. So you gotta be
Well,
careful
I
talking
mean,
about this.
words are powerful, right? Because some pens are mightier than swords, right? Anyways, so I want to talk about the history a bit. Why it's so well believed back in the days, right? And some now it's kind of a bit of a joke now for scientists, but I think it has really interesting model and history of it because it spanned thousands of years. So this kind of zodiac, astronomical zodiac, is like this imaginary, you know, group of what's called symbols or um, you know, quote unquote group of stars, right? So since it's been around, I think more than well, okay. Here's how it's gonna go. So the constellations come from like the names come from Middle Eastern, Greek, and Roman cultures. Even like also the Chinese has them, the Indian have them for a very long time, and the Babylonians were the first to apply these like god and goddesses or animal stories, myth to the star clusters. So it came with the 12 signs of the zodiac. But really, the origin came from, well, what were thought to come from like the Mesopotamian era, where they look at the stars and record all these stuff. But the actual oldest zodiac imagery was from actually around French. So archaeologists found these like Paleolithic cave paintings of like bulls, horses, and different animals with backgrounds that seem to have like prehistoric star charts. So this put like the zodiac back far as like 20,000 years old. So that is really long. And then the first record of astrology began in the for the Sumerians. So there was like the astrological history when one of the kings back in the one of the Sumerian king gathered the Sumerian astrology tablets known as the Enuma Anu Enlil. So these tablets are made of the first record of the zodiac. So basically, like the astrological document. And they name many of the constellations that give definition to the nature of the what they call the heavenly bodies. And then the Babylonians came along too. The idea that passed on from the Sumerians to the Akkadians to the Assyrians and now to the Babylonians. And they achieved this circular structure around 700 BCE, and with like wheels with planet and houses, that planets stay in houses and revolve around the earth. And the Persian actually evolved that further around 100 200 years later. So they actually create like birth chart and and locating planets within the zodiac. So not just stars, now we have planets. But the real big one, oh, I mean, they're all real, but the big one is in the 4th century BCE. And so the Babylonians kind of introduced um, astrology to the Greeks, and the Greeks applied this kind of animal circle to the zodiac, and all these big name in philosophy like Plato, Aristotle, also deeply thought about astrology, and it was thought as science at the time in the ancient Greek. So, and a lot of names for the planets and signs come from Greek mythology and their literature. So, and one of the pillar of Greek history or Greek culture was Alexander the Great, actually. So the um, the Alexander's empire basically export or propagate its Greek zodiac around the world because he did conquer a lot. So it actually brought this kind of Greek zodiac to kingdoms in Africa, even Asia, come to India, even though they've been there for a while already. So this kind of Hellenistic period that happens with the Alexander the Great and the Roman Empire kind of propagate this idea of zodiac wheel, and the Ptolemy is one of the kind of is there like mathematician which proposed this like geocentric, or like that the Earth is the center of universe, and it has been believed that for a very long time, right? And that's one of the main part of astrology. So that's why it's not very widely believed now. And the Romans also got into it too. And so when the Renaissance era came, the English Renaissance, around the 16th century, so the big time gap, and when people start to go into like early modern era or like late Middle Ages, this astrology start to get debated. So people start to doubt about it, and astrology has this like um, a lot of consultation that happens for like decisions were consulted with astrologers. They probably made a lot of money. And during the age of enlightenment, as a reaction to superstition and this stuff, you know, a lot of skepticism comes along, and science basically won. That we saw this kind of separation from astronomy, that from astrology, a new branch came out called astronomy. And once again, this astronomy basically destroyed this view of astrology that they had for a very long time. So this, however, in like the past couple hundred years, we have this new renewed interest in astrology, because this kind of is spiritual or mythicism that happened. This give like a new rebirth to astrology. That you know there are people, psychologists like Carl Jung, who pioneered the use of astrology in like psychological analysis. So it might be also not really about the truth of the universe, but the way people behave. And astrology can provide some insights to why people behave the way they do. Even now, like with the invention of the internet, astrology also has become more and more popular. They actually like a very extensive list of astrology classes and information on astrology. Anyone can look it up now, and you know a lot of people believe. Actually, in 2014, National Science Foundation poll found that more than half of millennials think astrology is a science. So, well, that is troubling, right? So even though there's this long fight and debate hundreds of years ago that we figured out that astrology is basically untrue, and it somehow resurfaced with this kind of propagation of information with the internet. People, comes to believe whatever they believe, and I think Carl Jung also demonstrated that there's something to it, even though that might not rely on the objective scientific fact, but there's something spiritual, quote unquote, going on when people talk about astrology and how it influences their life.
I guess if you like read a lot of astrology stuff and you're like, "Oh, I'm this sign or whatever. I'm this zodiac." It's gonna tell you you behave like this, and then you might start believing it, or you might kind of subconsciously start doing it more. And I don't know. I'm. It's so silly to me though how, like you said, it's kind of come back with, even though we have better access to information, it's like we also have better access to the wrong information.
Yeah, I mean, I grew up in the astrology kind of what's it called, society-ish. Like, we have like a very popular TV show with all the celebrities, and the theme were like celebrities who were born in this zodiac would come on, and they compete in this game show, but it's all based on like astrological predictions, like, oh, because you are in this zodiac, you are likely to be wealthy, and so you win the game or something like that. Like it's kind of hilarious, and it really, in a way, it helps me become a scientist, because like I was so doubtful of that. I was like, that is absolute crap. So that's why I thought, it's like, oh man, there's no way these are crap. But there are a lot of people who believe and love that show.
Well, I think one thing we can take away from this after Liam's final comment.
Oh, I saying before we end, what are your guys' zodiac signs? I'm a Cancer, which tells you everything you need to know about me.
Well, apparently, my zodiac sign don't get along with Cancer, man.
All right, this is the last episode, everybody. What is it though?
I think it's Sagittarius. No, it's Capricorn. I always get them confused. I know like my Chinese zodiac sign, and there's like
Oh,
the Western one,
yeah, yeah, okay,
and
okay.
there's like different ones, and there's Chinese also have a year one, and I don't
I
know.
think
There's like
mine.
all
I
these
think my Chinese
different
one.
systems.
I think my Chinese one is the bull, but I don't remember.
Oh, because year, right?
Yeah, yeah.
And but like I never really like put my mind trying to memorize it, so I was like, oh, whatever. I'll
No.
look it up. But
I've
yeah.
just had people tell me enough times that I now know, I guess.
Well, with
What's
that,
yours,
whether you
Patrick?
believe in, that's confidential.
Oh, okay.
With that,
okay.
we make sure to check your facts and sources, and thank you for joining us. Bye, everyone.
Take care.
Peace.